Namaste everyone. Welcome to the next tutorial of the course on image processing using Python. I am Dr. Atul Kumar Dwivedi, Assistant Professor from Bundelkhand Institute of Engineering and Technology, Jhansi. In this tutorial, I will talk about the advanced image filtering techniques. You remember in the last session, I discussed about Google Colab. You must learn how to work on it. And then what is the filter, how to apply the filter, what is convolution, how it works, what is the noise, how to introduce a calculated noise into the image, and then image filters, filters for removing the noise, process of filtering, applications of image denoising. The filters are not limited to the image denoising. Filters can be applied for the edge detection, filter can be applied for the deblurring process, filters can be applied for other purposes also, but I am focusing here on denoising. And I also discussed some basic filters like mean filter, averaging filter, median filter, Gaussian filter, etc. You can explore it more filters if you want. But in this session, I will take some advanced filters which are called non-linear filters because there was some problem in the previous filters. The major problem in the previous filters is that they are not able to preserve the edges which are important for object recognition of the images. Therefore, in this session, I will extend your understanding of the filters with the new and little advanced technique of the filtering with the help of topics like the bilateral filtering and transform domain filtering and morphological filtering, etc. Because these filters are little advanced, therefore I will take in detail. There are many advanced filters. I have chosen these to discuss with you. Because these are understandable and easily implementable in Python. We are focusing on Python implementation of the filters. And at the last of the lecture, as I usually do, I will discuss the conclusion, what you have understood, what are the outcomes of the lecture. You remember the thing that I told in the last session, that all the codes will be available to you. The advanced level filtering. And there is a long list of the advanced level filtering techniques available in literature. Some of the filters that I have considered in this discussion are bilateral image filters, then conservative type of image filters, then Wiener filter, and then a CCC algorithm, advanced algorithm, that also I will cover in this session. First one is bilateral image filtering technique. This blurs the image, smoothens the image, also considers the nearby pixel intensity values and considers the pixels on edge, that pixel is on the edge or not. So it replaces the intensity value of each pixel with a weighted average of intensity values from the nearby pixel. Here the weighted average come. I told that weighted average is better than the normal averaging, therefore it is also a better filter that compared to the mean filter. So the equation for bilateral filter is given by the filter image is equal to 1 upon WP, WP is the weight, summation, X is the summation of omega, IXI, AFR, XI minus LX, GX, XI minus X. So here this GX is the Gaussian function and WP is the weight, and WP is also calculated by, as I told you, that basically we take Euclidean distance, Gaussian function, depth distances, photometric distances. These all are included in this equation of weight calculation. And in this equation, I filtered is the filtered image, I is the original image, input to be filtered, and x are the coordinates of the current pixel to be filtered. Omega is the window centered in x, so x is the element of omega of another pixel. Fr is the image set of coefficients for smoothing differences of intensities. Fr is the for the intensities. This function can be a Gaussian function. Gx is the spatial domain or spatial domain kernel is for the smoothing differences in coordinates. This function can be Gaussian filtering. The weight is assigned, the weight value is calculated to this using this spatial closeness, using a spatial kernel, and also the photometric differences or intensity differences using the range kernel. Now consider a pixel located at ij that needs to be denoised in image I using neighboring pixels. So one of the neighboring pixel is located at KL, then assuming the range of spatial kernels to be Gaussian kernels, weight assigned for pixel KL to denoise the pixel ij is given by weight equal to ij KL exponential I minus j minus k square upon 2 sigma j, and exponential similarly, where sigma d and sigma are the smoothing parameters, I and g are intensity of the pixels, and the pixel is also can be evaluated. So if we apply this filter to the image, then we get a denoised image. So when the sigma r increases, then the bilateral filter gradually approaches to Gaussian convolution, and more closely because the range Gaussian widens the filter flattens, which means that it becomes nearly constant over the intensity interval of the image. As the spatial parameter sigma d increases, the larger the features get smoother. In this filter, there are two major limitations that can be introduced because of the several problems in the image. First one is staircase effect. What is that problem? In this problem, intensity lead to the image appearing like cartoons. Second problem is gradient reversal. So this introduces the false edges in this image. So there are some improvements that researchers have done in this filter. There are many improvements in this filter, like scaled bilateral filter that scales the image before for computing the weights. There are alternative filters. There are many books also available. One book is available in IEEE, published by IEEE, known as Bilateral Filtering Theory and Applications. If you are interested to understand the bilateral filter in detail, if you want to apply bilateral filter in your research, or you want to do research on bilateral filter, then you can read this book in detail. Let us go to Python. So before going to Python, you know already that you have to import the libraries, and then Google Colab. If you are using Google Colab, then if you are using the images from your Google Drive, then you need to mount the Google Drive folder before using it. For bilateral filtering, there is a built-in function available in OpenCV library of the Python. If you want, you can clear the previous variables, global variables if there are. I usually clear the variables first, and then I add the libraries. So NumPy will be NP, Pandas will be PD, CV2 will be CV, and Matplotlib will be PLT. You have to mount Google Drive by using command from google.colab import drive. When you click on the play like button available in Google Colab, then it will pop up a window in your screen that will ask that do you want to give the permissions to Google. Make sure if you want, you trust that you want to use the image in this program, then you can allow it. So click on the allow button. After that, your Google Colab notebook will work. Google Colab notebook have advantage that you can write the notes in that, you can write the titles in that, you can write coding in that. So all things in one place. And there are GPUs, free GPU available up to a limit, but if your program require higher order GPUs, then you need to purchase it from the Google. Let us come back to our filtering, bilateral filter in Python. In this session, I will take one special image of human taken from standard database known as KDEF database. This database is Karolinska directed emotional faces KDEF, which is a set of 4,900 pictures of human faces expression. So one image I am taking which have some noise, and this noisy image we will do. These images are available of 78 individuals, 35 women and 35 men, but we have nothing to do with the complete database. We need only one image. We will do processing, we will try to filter that image, apply filters to that image. So we will apply first bilateral filter into this image. For bilateral filtering, we have to initially read the image. So to read this, you can use cv.imread command, and for proper processing we usually resize the image so that the processing can be done properly, and we will know at every moment what is the variable size, how many number of rows and how many number of columns are available in our variable. That is what I am doing, and then I am using the standard bilateral filter available in this and applying to this. To plot, I am using the subplotting of matplotlib. So plt.subplot, and taking a figure size 10 cross 5. You can use other figure size also. Figure size is not that important, but if you don't use figure size, then there is a problem that there will be small images coming in the output. If you use this figure size, then a proper visible image will come. And then you can use imshow command to see the image. Then you can put the axis off, because axis should not be shown in the images. Labels on the axis, the points on the axis. If you want to try, you can comment the axis command x0.axis off, and then you can see the effect, what kind of effect is coming, and then setting the title, and then you can apply the filter. So blur equal to cv.bilateral filter. Here the bilateral filter is being applied. Then you can use ex1 imshow for the bilateral filtering. This will show you the image. You can see the image here. This is the result of the image. You can see that left side image is original image and right side image is filtered image. There is blur that is being shown here. Next kind of filter is conservative image filtering. The conservative filter are preferred to remove salt and pepper noise. It determines the maximum intensity within the neighborhood of a pixel. If intensity of center pixel is greater than the maximum value, then it replaces by maximum value, or this filter is also called maximum filter. Not conservative filter is called, no, there are two filters, one is called maximum filter, one is called minimum filter. In maximum filter, when you apply to an image, then it takes a neighborhood. Neighborhood means one pixel and nearby pixels. So when it takes the neighborhood, then the maximum value from the neighborhood is taken. So the maximum value of the neighborhood is taken and the pixel is replaced by the maximum value. and then it moves. Then again neighborhood is considered, and then whatever maximum value is coming, that maximum filter is also there. Minimum filter is also there, that we take one pixel and then neighborhood of the pixel. In the neighborhood, if anywhere the minimum value is available, that is taken and the pixel is replaced by the minimum value, that is minimum filter. So these both two are used in the conservative filter. The conservative filter preserves the edges of the image, but does not remove the noises like speckle. The filter is not able to remove salt and pepper noise also, but it is very nice filter. Let us first define the conservative filter. So here I am defining my own function. So for defining a function, you have to use def command, then conservative filter, then data is image data, and then filter size. I am taking one temporary variable, there is an indexer. So new image is data copy. This copy command is very useful. So if you want to keep the data, original data, you can store it using the copy command, data.copy. Then number of rows and number of columns can be taken by data.shape. The data is your image. So image.shape is giving you shape of the image, number of rows and number of columns. Then we will run two loops for one for number of rows, another for number of columns. Then third loop is there for doing the actual work, the one for doing the replacing the filter by the maximum value. So if the value in the row and column, if the pixel value is nearby pixels are having the higher value than this pixel value, then it will be replaces with the higher value. So in this way we have defined the conservative filter. Now it's time to apply it into the image. So I have read one image into the Colab and then into the Python, or for these code can be used in any Python IDE. So I have read it, then plt.figure, this will take figure size 12 by 12, any figure size you can take, that should be visible, and then subplotting. So 1 to 1, 2 subplot. 1 to 1 means I am taking two subplots, one row and two columns. Out of these, first one is for showing the original image. So I am plt.im show, this will show the first one, and also give title as plt.title, this will give title as original. X text blank, y text blank, this is also a similar command like access off. Then subplot 2, in the second plot we will say the image coming out of the conservative filter. So we will give title to this as conservative, and then I will show the image. You can see the results here in this. See the left side image, that was the original image, that is noisy, and right side image after conservative filtering, so much nice image. A lot of noise has been removed from that. Now let us go to another advanced level filter, which is called Crimmins complementary culling algorithm. In short we say CCC algorithm. This filtering is based on the algorithm. There is a process. Inside this process there are filters. So this is not out of the filtering. I am not going out of the filtering. I am inside in the filtering process only, or discussing the filters only, but this is the algorithm that uses the filters. This Crimmins complementary culling algorithm, CCC algorithm, is used to remove speckle noise. Also smoothens the edges. No, also smoothens the pixels, preserving edges. Preserves that. It also reduces salt and pepper noise. The algorithm compares intensity of a pixel in an image with the intensity of its nearby neighborhood. The algorithm considers four set of neighbors: north, south, east, west, northwest or southeast, northeast and southwest. Let ABC be 3 consecutive pixels, for example, in east, south, then we can understand the algorithm for each iteration. In this triple C algorithm, initially we do dark pixel adjustment and then we will do the light pixel adjustment. For each of the 4 directions, we will process the whole image with, if see the is A, B are the values of the pixel. If A is greater than B plus 2, then B is equal to B plus 1. Process the image if A is greater than B and B is less than C. A is greater than B and B is less than C, then B equal to B plus 1. Process the image if C is greater than B and B is less than A, then B equal to B plus 1. If C is greater than B plus 2, then B equal to B plus 1. Similar process goes for the light pixel adjustment. What will be the difference? In the dark pixel adjustment, we were increasing the values of the pixel so that all pixels become much lighter, and here in a light pixel adjustment we are reducing the value of the image so that pixels become the more adjusted. So we will process the image if A values of A are less than B minus 2, then B equal to B minus 1. If value of A is less than B and B is greater than C, then B equal to B minus 1. If C is less than B and B is greater than A, then B equal to B minus 1. If C is less than B minus 2, then B equal to B minus 1. Okay, so in this way you can, I have coded it. The code is available on my GitHub repository. The detailed code is available for this triple C algorithm. The function name is given as Cremens for the first scientist name, and then here I am calling the function and giving img underscore o as input. Plt.figure will take the figure size. Figure size is taken as 11 by 6. Then the two plots are required, so subplot 1 to 1 and subplot 1 to 2. I am using this. In the upcoming after some time I will use something else for, so that I will use one function for that, so that every time you do not have to write this plt.subplot and plt.subplot, plt.subplot and then I am so for the every image. I will make one function and this function we will call every time, so that you have to write only the titles of the images. And so here in the first one there is original image, X-ticks and Y-ticks both are removed, and the title of the second image is given as triple C filtered. Here also we have to remove both of the ticks. When ticks means the points coming out in the x-axis and y-axis, and then plt.show is important because for the subplot it will not show until you write the show command. Okay, so you can note it down that here I am using imshow command from the matplotlib library that is called here as plt. See the result of this algorithm, this filter. The original image is here in the left side and the filtered image is in the right side. You can see that there were many noisy pixels in the face of the person, and that is removed because of this filter. Now let us go to the transform domain. You all know that convolution in time domain results in multiplication in the frequency domain. You must have studied a mathematics course or signal processing course. If you have not gone through, you just go through that. Fourier transform or the jet transform, discrete Fourier transform, discrete wavelet transform. There are many transforms available and that are very useful. At the time of studying you might not have be knowing that what is the use of this transform, but here I am telling you how can you use this transform for images. That you will see that these transforms are very useful for image denoising. Your work of convolution, that is very complex. Convolution is having 4 operators. addition, then shifting, then multiplication, then summation, 4 operator. And but this convolution in frequency domain get converted into multiplication, one single operation. That is what is the advantage of transform domain. Because of the complexity of this space domain, there is more computational time in calculating the convolution as compared to the frequency domain filtering. Frequency domain filtering is faster. So, how to get converted? The image need to be converted to frequency domain before we apply filters in frequency domain. So, the process is transform, Fourier transform, discrete, because image is discrete. So, this will be discrete Fourier transform. Why we are interested in the frequency domain representation? Because it is only the multiplication, because each pixel in the frequency domain corresponds to the filter in the location of the image. See, in the frequency domain, the representation of image also will be different, because in the frequency domain you will be able to see the repetition of the pixels rather than the location, means the spatial distribution of the pixels. This is the due to fact that each pixel in the frequency domain corresponds to frequency rather than the location of the image. The DFT command of NumPy library can be easily applied to the image. This will determine the discrete Fourier transform of the image. The Fourier transform, when it was invented, might not be, image processing was popular at that time, but nowadays that Fourier transform that Fourier did a long time ago for the some heat convention or heat equation problem, for solving heat equations. His purpose was not that it will be used in image processing or video processing, but nowadays people are using. So, what it does? The Fourier transform decomposes a signal or image or a video into the sine and cosine. This is the extension of Fourier series. In Fourier series you have seen that the signal is divided in DC, sine and cosine. Here there is image, so it is 2-dimensional signal only. So, 2-dimensional signal also will do the same thing, will decompose the function into sine and cosine. It can be applied to an image to obtain its frequency domain representation. Okay, so let us consider an image of m cross n size. 2-dimensional discrete Fourier transform of this image is given by f r comma c, means the row and column R C is the row and column, f capital F represent the Fourier transform, summation I equal to 0 to m minus 1. Here the index is starting from 0 to m, m is the size of image, j is the column, we are going to columns from 0 to n minus 1, Fij is the image to which Fourier transform is being applied, e to the power minus 2 pi ki upon m, k lj upon n. So, again mn are, m is the number of rows, n is number of columns, and I r and j are indexes. So, if this function, if this equation is applied or computed on an image, you can write function if you want for this, but there is a ready function is available in NumPy library. So, if we use IMSO function, then for this Fourier transformed image, then there will be amplitude spectrum available to us. I will show you. In order to get our image back in a spatial domain, we have to do what? Inverse Fourier transform, natural. Inverse Fourier transform is also available. So, what is the equation for inverse Fourier transform? If I have a image of size m cross n, means m number of rows and n number of columns. So, then Discrete inverse Fourier transform is given by, see this output is small f means space domain 1 upon m cross n. This is m is number of rows, n is number of columns. Again k equal to 0 to m minus 1, index from 0 to number of rows. L equal to 0 to n minus 1, index from 0 to number of columns. FKL, here it should be could have been capital, but FKL is the Fourier transformed. FKL is a Fourier transformed data of the image, and then e to the power 2 pi kx upon m L b upon n. Okay, so b x and b x a and b are the resultant. So another converting back to the space domain, if we use IMSO function, then original image can be seen. After converting this, you will see the original image. There is no problem now. Okay, so for the Fourier transform, I am using a function called DFT from OpenCV library. In OpenCV library, DFT function is available. So, but before applying this DFT function, we have to convert the 64-bit image that is represented in unsigned integer to a float, because this DFT function is applicable only to the float kind of data type. Therefore, we have to convert this unsigned integer 64-bit data type to float data type of 32-bit. Okay, then you have to apply one important thing, shifting the zero frequency component to the center of the spectrum. What happens when we apply this shifting? The zero is padded, zero padding is done. Because of that, the zero location is shifted, so we have to shift it back to the proper location. So this DFT shift is important, that is required for doing anything, before doing anything to this image. Then we can save the spectrum. So if I want to visualize the spectrum, if you want, because in Fourier transform there is a real data and there is a complex data also. So if you want to see the magnitude spectrum, then we have to take the log and magnitude. So then we have to plot both of the images using the, I am using the subplot command, and then I am also using 1 to 1. So this will show the first image, and then 1 to 2 will show the second image. So second image, first one is showing the input image, and second image will show you the magnitude spectrum of the image. You can see the results in this. See the image, left side image is there and right side magnitude spectrum of the image is there. You can see at the middle of the right side image there is a white bright color. What it represents? That there is the highest intensity. You can think of the distribution that is available for the, it's a Fourier transform. So it is showing that the brightest intensity is available at the middle point. Now what I am doing, that I am designing a mask, and mask for what? For filtering purpose. Okay, so I will first of all calculate the shape or size of the image, and then the mask is means for mask I am taking initially the 0 values. So mask equal to np dot zeros. Zeros, how many zeros? Number of rows and number of columns, and of type uint 8, unsigned 8, uint 8, or type of images are, image is having data type uint 8. Therefore uint 8 is written here. And then what is done, that we are making 1 to the number of rows minus 30, to means there in the middle I am making some pixels as 1. You can understand that. So what it will do, it will create a bright square. The value is 1 will be white and 0 is black. So for that it will create a bright square image. I have already shown this bright square you earlier, and this bright square I will apply the mask. So F shift equal to DFT shift into mask. So DFT shifted image, whatever is available to you, you can multiply the masks to it. Why direct multiplication is applicable here in this line? You can say masks and inverse DFT. So DFT shift into mask, this is multiplied, and then FFT shift is again, and then image back. For getting the image back, this is, you can see the image img underscore back, this variable is having the inverse DFT. After inverse DFT, we can take the magnitude of the image IDFT, that will represent the filtered image. So that is how the filtering is performed in the frequency domain. I have in this last 4 lines are for plotting purpose, for displaying the image. I am using this subplot and then plt.imshow, then showing the first one, then showing the second one, like that. Low pass filter, this bright square is a low pass filter which have intensity 1 in the middle and 0 at after certain point. So you can see that input image is having more noise as compared to the low pass filtered image. One filter called Wiener filter, and this there is a special filter. Filtered image using Wiener filter is given by f of ub equal to h of ub upon hub plus k gub, in which f of ub is the estimated and gub is the degraded, and degradation function is there, complex conjugated there. This is the program for Wiener filter, defining the Wiener filter. This definition, all the definition is written using the equation that I have just shown to you in this. Okay, well, I am leaving this, writing this function for you for exercise. You can write your own. This you can apply this to the noisy image as I have applied in the last discussion, and you can see the both noisy and denoised images together. Now last kind of filtering that is very useful for image segmentation called morphological filtering. Morphological filters are very useful for the segmentation purpose, and there is specialty about these filters is that they are having the coefficients depends on the nature of the operation. The morphological filters are the filters that are based on the shape of the image and structure of the image, and that are very useful for the segmentation. There are two kinds of basically morphological operators, or operators are also word used for the filters. So morphological filters are two kinds, one is dilation, another is erosion. Erosion is just like soil erosion, it erodes the boundaries, it wants it removes away the boundaries of the foreground objects and tries to keep the foreground white. So the operation follows the coefficient kernel slides over the image, and the pixel of images are considered one only. If all the pixels are under the kernel are 1, then they are 1, otherwise it is eroded. So the kernel is np.1, it will create the 5 by 5 matrix having value is 1, and for erosion I am using the predefined function C of the OpenCV library cv.erode. You can apply this filter to the original image and do not iterate. If you do not want to iterate it, then write iteration equal to 1 and then plot the figure, original image and the eroded image both can be shown by using this function. See, the left side image is the input image, and when erosion is applied you can see that black pixel and white pixels, the image is something changed. So you can see that you can say that, sir, this is not doing the good thing, this is not a good filter, you see the image is something, but you can see this is a, you just this time you just take it as a one filter. It will be useful when we discuss image segmentation. Dilation is another filter which is opposite to the erosion. Here pixel is considered as 1 if at least one pixel is under the kernel is 1. In this case it increases the white region of the image. Dilation is very helpful in joining the broken part of the objects. Here I have used OpenCV library of the which dilate command from the OpenCV library. Similar to the erosion, you can apply the dilate command and you can show both of the images using this subplot command. You can see there is more whiter, the image is whiter, many points of the image which were black initially are now white. So that is now I can conclude it as in this session or in this tutorial what we have understood. We have seen some advanced filter, advanced level filter, advanced Gaussian filter which is called bilateral filter. Then we have seen a minimum filter, maximum filter inside this bilateral filter. Then conservative filtering, triple C algorithm for the filtering. After that we have seen the Fourier transform domain, not Fourier only Fourier transform but for any transform domain filtering and the only multiplication, and then we have seen the erosion and dilation morphological filters. Although I am ending the session here, but this is not the end of advanced filter. Because of the time limitation I could not go beyond these limits, and but you can explore the advanced filters like Kuwahara filter, accelerated graph based spectral polynomial filters, nonlinear iterative filters, Chebyshev filters and conjugate filters, etc. Again I will remind you that you can get the codes related to this lecture on my GitHub repository. The address for my GitHub repository is github.com/Dr.Atul/image filters. Filters for edge detection will be discussed in the next session. I hope this session would be helpful to you, would have given a important information to you, and thank you all. Happy coding. Meet you again in the next session.